The aim of the CETIEB project is the assessment and improvement for indoor environments in retrofitted and new energy-efficient buildings.
One major objective is the development of advanced monitoring tools based on a wireless system. The case study, being the Richard von Weizsäcker School in Öhringen, consists of a complex of 3 buildings. 2 buildings, connected by a central hall, are to a passive house standard, and the third is to an energy-efficient standard. The school is equipped with solar panels for energy generation and has advanced installations for education in natural sciences. The windows in the passive houses cannot be opened due to problems with the window framing. Therefore, the air exchange is only realized by the central ventilation system. Some teachers and pupils complain about irritations, such as headaches, overheating and cold drafts. To identify the reasons for these complaints, the project assessed 2 classrooms in a monitoring campaign, one facing south and one facing north. Both classrooms were equipped with advanced sensors, and in each room the following parameters were measured: CO2 at 2 positions, total VOCs, the volatile organic compounds, thermal comfort and the effects of illumination and heating by the sun, ventilation air velocity, as well as temperature and relative humidity at different positions. Additionally, data from the school weather station on the roof were incorporated into the project database for comparison and assessment. The results of the monitoring helped to improve the quality of the indoor environment in the school. The sketch shows the position and actual measured values of the sensors in the suddenly exposed classroom A2.06, as represented by the real-time online visualization tool of the monitoring database. It includes several temperature and humidity sensors distributed throughout the room. 2 CO2 sensors in the center and near to the whiteboard, a sensor for wind speed at the ventilation outlet and light sensors at the windows. The sensors are operated by sensor nodes equipped with batteries. The monitoring system can run for up to several years, being dependent on the power consumption of the attached sensors. From time to time, the monitoring system must be checked to maintain proper operation and to avoid data loss. Behind the wooden grille is the central ventilation outlet, where a sensor node equipped with an air velocity and a combined temperature and relative humidity sensor is attached. Exchanging batteries in the sensor node is being performed. In the sketch, the position of these 3 sensors is marked by a circle. In the screenshot, the signal for air velocity sensor shows clearly the timing and speed of the air coming out of the ventilation system. The wooden platform suspended from the ceiling in the center of the room is equipped with different sensors. A total VOC sensor array from Fraunhofer IPM in Freiburg, comprising 4 different VOC sensors, and a sensor node with an integrated CO2 sensor from product partner TTI SmartMote in Stuttgart. At the bottom of the platform, a thermal surface sensor from product partner Università Politecnica del Marche in Ancona is installed. The so-called Comfort Eye infrared sensor scans the walls and floor of the room and estimates the mean radiant temperature of the scanned areas. From this data, the so-called predicted mean vote or PMV value is determined. The PMV is a measure for thermal comfort in a particular area. By assuming the activity and clothing of a person, different values are obtained. For example, the PMV is different for a pupil sitting or a teacher standing. The sketch marks the position of the sensors on the wooden platform, and the screenshot shows data from one of the TVOC sensors. Behind the whiteboard, a second CO2 sensor is installed. The same node reads temperature as well as relative humidity at the ceiling. A circle marks again the position of the sensors. The database screenshot shows a comparison of CO2 concentrations behind the whiteboard and in the center of the room. The time of day for the lessons appear clearly with peaks of up to 1500 ppm. At the windows, light and temperature sensors are placed to assess the effects of illumination and heating by the sun. The identified sensors are compared in the next database screenshot, where the temperature of the illuminated sensor in red is clearly correlated with the light intensity in blue. The northerly exposed classroom is equipped with the same series of sensors. The positioning was chosen to be as comparable as possible to the southerly exposed classroom. Within this project, the project partner DWE EcoCo in Dublin developed a plant-based air biofilter. The aim was to improve the indoor environment quality by filtering air through the root zones of particular plants, which were selected according to their efficacy. The scheme on the left explains this process. Contaminated air, see the red arrows, is sucked through the root zone into the center of the filter. Microbes in the roots of the plant remove VOCs from the air, which is shown by blue arrows. The tube in the center collects the refreshed air, and finally a low noise fan provides clean humidified air to the room. As a consequence of the cleaning effect, less fresh air is necessary, and therefore the energy demand for reheating or cooling fresh air is significantly reduced. A thermal insulation plaster system was developed by the project partner Schwenk in Karlstadt. The final finish of this system contains titania attached to perlite to obtain photocatalytic behavior. The attachment process was validated on a pre-industrial scale by the project partner S&B in Athens. To test the performance of the developed products, samples are placed in a test chamber and exposed to air containing certain amounts of nitrous oxides or VOCs. These tests were performed by the project partner IFK at the University of Stuttgart. Titania, a common name for titanium dioxide, catalyzes the oxidation of nitrous oxides or VOCs when irradiated with ultraviolet light. The advantage of expanded perlite, an amorphous volcanic glass, is its high porosity and opaqueness. Light and air can reach titania easily through the porous perlite matrix. This effect reduces significantly the quantity of photoactive titania required, a very costly product. The first step is to measure the concentration without light until stable conditions are obtained. When a constant concentration is reached, the sample box is exposed to light corresponding to normal daylight behind the glass window, which still contains a small amount of ultraviolet light. The photocatalytic reaction causes a drop in the measured concentration and demonstrates the effectiveness of the developed product. Project partner National Taiwan University for Science and Technology developed a natural light illumination system. Sunlight is collected through mirrors or directly by special elements called sun Lego, which guides the light through light pipes or optical fibers into a house. Inside, the sunlight can be used to illuminate dark rooms without the need of electric light. This technique is especially useful for equatorial or Mediterranean countries where the sun shines almost vertical during the day, and houses are shaded by large porches. The developed sensors were validated and compared with modelling results in a special environment at the Institute for Building Energetics at the University of Stuttgart. The institute possesses a test room with fully controlled ventilation and temperature controlled walls, which is almost unique in Germany.
In CETIEB project we investigate contaminant distributions in an office room with mixed ventilation. In rooms with mixed ventilation, contaminants are spread mainly by removing air. That is why we pay so much attention on air flows in the room. In our test chamber we can set up all surface temperatures and create necessary boundary conditions. It is important for us to have this possibility because we validate our simulation result with our measurements and the conditions should be nearly the same. Now we will go inside and see our sensors and installations. We apply person simulators which emit the same amount of sensible heat as a person. We do measurements in different points inside the room. Here you can see the sampling tube for a test gas and a temperature sensor. We also apply omnidirectional anemometer. Normally air velocities are very small inside the room. They lie under 0.2 meter per second. That is why we apply very sensitive anemometers that can measure air velocities above 0.01 meter per second.
The sequence shows a test using artificial fog in an office situation to visualize air movement in the test room. The fog is introduced through the ventilation shaft in the ceiling. The simulation of air movement fits well with the experiment. The center of movement is shifted to the right because of upstream warm air generated by the heated dummies on the left, which simulates sitting persons. The second simulation depicts air movement after the fog has reached all parts of the room. The consortium consists of 15 partners from 6 European countries and Taiwan. It is well balanced and technology driven with 6 small and medium enterprises, 3 large industrial companies and 6 partners from academia and research centers. At the final meeting in Stuttgart, the partners discussed the results and the overall impact of the project. The presence of the partners was also used to hold a public training workshop for professionals in Stuttgart and disseminating the project results.